to emphasize the interaction of the pieces is not always so easy. So now, the form of this limit. What do I mean by that? I'll make it pink. Color is always helpful. I have a numerator, and then I have a denominator. I am now, when I talk about the form of the limit, I'm not right away attempting to answer the question. I'm simply asking, how do these pieces behave on their own? Forget that they're combined in this function. Just how do they behave? How does the pink guy behave? If x, of course, approaches infinity. Well, that's just a polynomial. Its leading term is 2x squared. It's going to approach infinity. Again, we're building on our discussions of polynomials that have to be solid for this to be as easy as possible. How does the blue polynomial behave? Just on its own, as if it was a completely separate question. Well, its leading term is x cubed. X goes to infinity, so it'll go to infinity as well. Infinity. So now I see that the interaction of these two pieces is they're both increasing in size. And it's a question of how fast are they increasing. If one is increasing faster than the other one, it'll eventually dominate the whole thing. Infinity is not a number. I can't just say, oh, I'm going to cancel the two infinities and it equals 1. No. 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 Hello, everybody. Let's remember what we did last time. Let me just go to our problem book 1 second here. It's bigger. Now let's just see where, zoom out here. Where are we? We're at limits, right? Okay, so what did we do last time? Can anyone remember what we did? We talked about infinite limits, right? Where it's just another way of talking about the long-term behavior of a function. So we looked at problem 2.1. Correct me if I'm wrong. I don't quite remember what we did yesterday. Pretty sure we did infinite limits. 2.1, right? So there are two main function types to introduce limits. Polynomials, and we learned that the leading term, whether I put it in limit form or just ask for the long-term behavior, doesn't matter. The question is the same. I look for a polynomial at the leading term, and that decides how it's going to behave. Now it's going to go to one of the infinities. I just need to check. For example, number 5 here. X goes to negative infinity, but I have 4 of them multiplied together, so it'll be positive times another positive 2, so it'll be positive infinity. The issue is really, let's leave the roots for now. The issue is really when we get to rational functions, things get a little bit more interesting. Number 12, you said. Yes. Now I can't remember how far we got into 12. The problem here is now we have the relationship between these polynomials in the numerator and denominator, if you remember. Number 12. Individually, I know what they're going to do. Screen over here. Individually, I know what they're going to do. And when I look at pieces individually, we call that looking at the form of the limit. So the form of the limit in this case is infinity over infinity because the numerator goes to infinity, it's a polynomial. The denominator goes to infinity, it's a polynomial. However, infinity is not a number. And I can't say, oh, infinity cancels the bottom infinity, so it's equal to 1. That's not at all the case. These things are much more complicated. Can't say infinity over infinity is 1. Never. The answer might be 1 in some cases. Most often it won't be. It's an interaction of how the numerator and denominator behaves relative to each other as x grows in size. Now, the form does tell me something that I need to be careful. I don't know what's going to happen, and we're going to get this more and more and more as we go in the next couple of days. But I can't always just look at the form and simplify and know what the answer is. Sometimes, not always. So, because I have two polynomials, I can simplify that to say, well, long-term behavior of the top one is its leading term. Long-term behavior of the bottom one is its leading term. And now I've simplified the behavior of the original to be the same as the behavior of this much simpler polynomial over polynomial where I can cancel some x's. It simplifies much more easily, and I get that the behavior of the original is the same as the behavior of 2 over x. And we've seen that before when we looked at our basic rational functions, simple transformation of the 1 over x function, right? And I know the 1 over x function behaves as a horizontal asymptote, far to the right, far to the left. It doesn't change that. So my answer, the behavior of this guy is 0, and therefore the behavior of the original is 0, and the limit exists. It's how these guys interact that isn't obvious in the beginning when I have it in the original form, but because I'm only looking at behavior, I can simplify it to the behavior of something that's easier to identify. And in this case, this whole function heads to 0 as x gets really big, y value approaches 0. I can't look at the form and always from that see the answer. Infinity over infinity, that's not 1, it's not a number, they don't cancel. There are different levels of infinity and all kinds of stuff. If I look at the degree of the top polynomial, it's a quadratic polynomial. It grows like a parabola. But the bottom one is x cubed. It grows faster. The bigger x gets, the faster it grows. So the bottom one will eventually outgrow the top one. Yes, they both go to infinity, but at different speeds. And the form doesn't really represent that. I need to simplify it to really figure out. And in this case, because the bottom one outgrows the top one, eventually the whole thing will become a fraction shrinking down to 0. So the form is helpful to get a little start and see, okay, how do the pieces behave? How do I now proceed? Infinity over infinity, we'll see more and more. Really anything can happen. So I then know to be cautious and I can proceed by trying to identify how the individual pieces behave and then simplify that. So that's our problem 12. And of course, we just have to do more and more problems as we go. So these just pick up exactly where we leave off from last time because we have so many examples to get through. Let's see how it goes from now on, but let me know if you have any questions. Maybe he has a nose. He should have a nose. Okay, that's not the case. All I'm saying is sometimes when I look at the pieces individually, they could highlight what is happening and they could not. In this case, I have an infinity over infinity. We call that an indeterminate form because it doesn't really tell me how the whole thing behaves. It's all about how each piece, how fast each piece blows up That'll determine the interaction. So then I need to go and say, okay, at least I know I need to be careful. Infinity over infinity doesn't really tell me much. Now let's go and see, oh, it's a rational function. Okay, so let's look at the leading terms. And it turns out that the bottom one dominates, shrinking the whole thing to zero. But if these two were flipped around, they still both grow, but the blue one grows faster, and the result could be very different. Okay, let's look at, I guess I should stop, but I don't want to. I'm so close. I want to do this last one because that's sort of my point of this whole form thing right now. And again, I'm trying to introduce concepts like the form of a limit early because it's going to come up again, and it's, in my opinion, extremely helpful. Number 8 is the limit x approaches infinity 1 over root x minus 100. That's not a rational function anymore. What do I do? Leading terms? What's the leading term here? I don't really know. It's not quite the same. The form of the limit can very often show what is happening here. Well, the numerator is always going to stay at 1, right? Nothing's happening to it. There aren't any x's in there. What is happening to just the bottom guy? Just the denominator. That is a transformation of my basic square root function. It's the square root shifted to the right. Let's draw it. Here's my basic square root, transformed to shifted to the right. Which way is it going when x gets really big? Infinity. Basic transformation. Basic function. Now I have a situation, even though the function was something that I didn't know what to do with, it wasn't a rational function or anything, I have a situation very similar to this guy, where I have a number over something that blows up in size. It doesn't matter what makes it blow up in size. If the numerator doesn't match it, the whole thing is going to shrink to zero. Zero. I don't need to know the details of this function. It's not a rational function. Who knows what this looks like? I don't know. And I also don't care. By looking at the pieces separately, very often, not always, but very often, it can shed some light on how the whole thing behaves. If the numerator stays constant at 1, but the denominator keeps getting bigger, then the whole thing is going to be a fraction that shrinks down to 0. It doesn't matter what the function looks like. So by looking at the form of the limit, I'm looking at how the pieces behave separately, and if that could shed some light on the overall behavior. And very often it does. Of course, we need to look at this with a lot more examples. Tomorrow is a discussion on its own, but the idea of the form of the limit is going to come up over and over. It is so useful. I cannot stress how useful it is. Even if I get an indeterminate form of infinity over infinity, that still tells me, okay, be careful. Go look at the type of function and try and do something else and see what you could do. Even a word of caution is information that helps me. And sometimes it's so useful, it gives me the answer right away. This is not an indeterminate form. An indeterminate form is one where the form does not tell me the answer. Look at this. This indeterminate form came from this rational function, but if I flipped it around, let's note here, if I looked at the limit, same x behavior, but I flipped the numerator and denominator. Plus 23x plus 1 over 2x squared plus x minus 3. The form is still infinity over infinity, right? They're both individually going to infinity. They're polynomials. However, the answer to this limit, when I look at the behavior of the leading terms, it's going to be infinity because there are more x's at the top than at the bottom. So even though the form is exactly the same in appearance, the answers are very different. Different answers. So an indeterminate form, informally speaking, is when the form does not give me the answer right away, and many things could still happen. And we'll see that the only indeterminate forms are infinity over, well, for us, there are others. For us, it's infinity over infinity, 0 over 0. We'll see 0 over 0 tomorrow. Those ones, really anything can happen because it's all about how they interact with each other, how fast they grow, how fast they shrink down. Other forms, like 1 over infinity, it's not called a determinate form, but I guess you could. It's just not an indeterminate form. I guess you could call it a determinate form. That sounds weird, though. No one uses that. Sometimes the form gives me the answer right away. Boom, it's 0. Has to be. I don't care how fast this is growing to infinity. If the top one doesn't even remotely try to challenge it, the whole thing's going to shrink down. It doesn't matter how fast it happens. But I, I don't want to go on a rant, but if you read calculus books, even life sciences or more formal calculus, doesn't even matter. They don't give enough attention to what we're really doing here. It's all an interaction of the pieces to investigate the behavior. And sometimes it's super simple. There's nothing to do. And sometimes it's not, and I have to be careful. Fair enough. But it's all about looking at this in the most efficient way. What is this really saying? What are the pieces in my function? How can I use those pieces to get more information, to see which way this is going? If I just look at this in the correct light, it really doesn't have to be complicated. And it baffles me why I don't know of any textbook that does it this way. And they make it so much more complicated than it needs to be. It doesn't need to be complicated. If we just remember that we're investigating behavior, and of course, the pieces of the function will determine that behavior. And now it's just a matter of seeing all the little variations and building up our experience to not be surprised in a future problem. Lots of little things. The more I think about this, the more there are just little things that I need to see, that I need in order to form a big picture around what limit questions I have to be ready for and understand. Not worry. So, what have we done? We have done something. Let's see here. So far, we've looked at infinite limits. That is where I like to start because it emphasizes the behavior, infinite limits as a long-term behavior question. And because we're taking a slightly informal approach to limits, it's very important to understand what they are trying to express in the mathematical language. It's all about behavior, asking the behavior question. Now, for example, limit as x approaches infinity of, let's say, 2x over x to the 5 plus 1. Random example. We've also introduced the form of the limit, which can quite often help me figure out how the pieces interact. Or worst case, tell me that there's a little more to it and I need to take another approach. Either way, it has information and I always want to do it. But it is a little hand wavy, right? What I'm doing is look at, okay, how does just 2x behave as x goes to infinity? Okay, infinity. It doesn't tell me how fast or anything really, but it tells me that it is growing as well. X to the 5 plus 1 also growing. Now, that's not a number. The risk, I guess, is when I write something like this, there are people, regardless of my best efforts, there are people that think, oh, infinity over infinity, I cancel them and it's equal to 1. Well, I mean, at some point, I just can't help you anymore because nowhere in your math schooling has anyone said infinity is a number, and it doesn't follow the same rules. It is simply an indication of unbound growth. It doesn't follow the rules. So when I write it like this, it might be a little deceptive. This is just for us on the side, unofficially, to investigate and get a little bit more information as to what this function is all about. Okay, so see it for what it is, and we'll be fine. So this then tells me, oh, infinity over infinity, they're both growing. I can't really conclude anything because it's then a matter of how fast they're growing compared to each other, which means I have to go and look at my function. In this case, it's a rational function. That means I compare the leading terms and its behavior under these x conditions is equivalent to the behavior of the ratio of leading terms. I can cancel one of those x's, leaving 4 at the bottom. More x's in the bottom, constant in the top. I can do the form again. Form of this is a constant 2 for the numerator and something that blows up for the denominator. Well, now this form tells me a whole bunch to the point where I don't have to do anything anymore. If I have a constant at the top and something that blows up in the bottom, this guy is going to shrink to 0. There is no other way. So see how I can always use the form. Whatever limit I have, the form tells me something. It could be very good news. It could be just news. Either way, I have more information. So it's definitely something I want to keep in mind. So infinite limit, meaning x approaches plus or minus infinity. Not the answer is in infinity. The answer could be whatever it wants to be. I don't care. Okay. But of course, then it's reasonable to say, well, uh, I could ask the behavior question for x approaching a specific number. It doesn't have to be far to the right, far to the left. So let's see. So let's just make an example before we go to the problems. The example I have is y equals 1 over x squared. Now, I'm going to draw this for you. It's not a basic function that we have because it's not a transformation. It's not one of the simple transformations of our rational function, even though this is a rational function. The graph looks like this. And you can plug in some numbers and convince yourself, and it's not overly complicated like that. So we see that apart from the long-term behavior question, there is an interesting thing happening as I get close to 0. This function is undefined at x equal to 0. However, there is predictable behavior as I get close to 0. The function is, I'll make a big is defined, I'll casually say around x equal to 0 on an interval containing x equal to 0. Though at x equal to 0 specifically, we have a little bit of a problem because we can't divide by 0. We don't have a y value. Anything around even 0.00001, I have a y value. I just can't be at 0. I can be as close around 0 as I want. There's a graph everywhere else, which means I can investigate behavior everywhere else. as I get closer to 0. So now the question is, as x gets closer, I'll put here brackets, around 0, how does the function y behave? That is the question. All right, sorry about that, but it gave you time to think about this. Okay, so there is behavior that I can describe with this. So let's say here the answer is y, let's say, grows in size and is positive. So it's not a difficult thing to observe, especially once I have the graph, right? I now simply want to translate all of this into my mathematical language. So we're going to say, well, limit is our mathematical word for behavior. The behavior of my function, and I like to see the detail, though you could call it just y, as x approaches 0. This is now a finite limit because of what x is doing. X is approaching a finite value. Okay. As we see on the graph, unbounded growth, the closer, regardless of where I am, right? The closer I get to 0, the more the y value blows up, the higher the graph goes. But it's predictable. So we can write an infinity there. Still, as we mentioned yesterday, limit does not exist. In this case, this is just a simple first example. We're going to see a lot of examples. If I get a number here, that means the y value can be contained within a small range, and that range gets smaller as I get closer to my desired x value. It sort of stabilizes closer towards a specific number. Great, limit exists. But sometimes there's unbounded growth behavior. I can still indicate that, and we've discussed this yesterday. Don't read too much in the equal sign. It is an appropriate symbol to use. That does not mean it exists because of this infinity that I have there. Okay, so the step towards finite limits is not a huge step. I only look at x doing other things, approaching specific numbers perhaps. Not a big deal. Let me just check here. I wanted to do 14, so why not? Okay. While I'm here, I might as well, I don't know if I want to do it right now. I might as well, yeah. Look at the form of this limit. I can always do that. Why not always then do it? Well, I have a constant at the top, 1 in this case, and my denominator, when I look at it in isolation, approaches 0. Again, that's not a calculation. 1 over 0 does not equal infinity. If you say that, I'm going to ding you. I'm going to subtract marks because it shows a lack of understanding, and that's never something I'm going to write. However, the behavior of a fraction with a numerator of 1 and a denominator that shrinks down close to 0, the behavior tends to infinity. It goes to infinity, that function. So we say the behavior is infinity, though that's also a little relaxed. 1 over 0 is not infinity. I will never write that. So you shouldn't either. I say that because I see people do it. And then you feel cheated when I just start subtracting marks because I can't confirm that you understand our language here if you just abuse it. So you have to be careful how you write things and how you say things. When I ask about the behavior of a function, this limit portion must be in front, always. I see people just scribble some stuff like, okay, like this. Maybe you want to scribble some stuff there. No, then I read that, and that's not right. You can't do that. Okay, but this is a new form where the numerator is constant. I have a denominator that gets smaller and smaller and smaller and smaller. Plug in numbers. 1 over 0.1, 1 over 0.01, 1 over 0.001. The whole thing blows up. So you can convince yourself that this form does give me a lot of information as to what the limit does. Okay, so I want to do problem 2.2, number 14. Let me just resize this. Problem 2.2, number 14. And of course, ask your questions as you think of them. Don't wait for me to pause and check. 2.2, number 14. 14. I zoom in. Zoom. Ah, you can zoom more. There we go. 14. Nice and big. Very similar function. Limit x now goes to 2. X approaches 2. I already forgot the function. 5 over x minus 2 squared. So the first thing I should check, I want to get into the habit, though rarely it's an issue, I should check it. Is this function defined around x equal to 2? It doesn't have to do anything at 2, because as we saw in this example, scroll down, I'm actually never going to be at that x value. I can't be. Yet I can still ask the behavior question. So actually, the behavior question is not concerned with what is happening at that x value. It's concerned with what is the graph, what is the function hinting at, which way is it going as I get closer to that x value. I will never be there. So we therefore only require that the function is defined around the x value, not at the x value. It could be, it could not be. I could not care less, to be honest. That's not a part of the discussion. The discussion is about what does the rest of the function tell me it wants to do as I get closer? How does it behave as I get closer? What actually happens there is irrelevant. So now I can look at the form and it tells me everything. I have a top staying constant at 5. I have a bottom doing what? On its own, x minus 2 shrinks to 0. So squared also. Question in the chat. Would we expand the denominator even though we know the first term is x squared? Would we expand the denominator even though we know the first term is x squared? That, no. I only have that specific, I think that's what you mean. I only have the specific technique of looking at the leading terms when it is an infinite limit. This is not an infinite limit. Different question. This is not a long-term behavior question. Though it's still a behavior question, it's handled completely differently. The finite limits are not handled the same way. Only the infinite limits. In rational functions, it's a comparison of leading terms. Long-term behavior of polynomials are dominated by their leading term. Short term, no, it's a mess. It could be anything. And this is a finite limit. But I can still look at the numerator and denominator in isolation to help me figure out how these two pieces might interact. And in this case, it actually tells me a lot. Remember, it's not a guarantee that it will. In this case, however, I have a numerator staying constant at 5. I have a denominator shrinking down. It's not 0. It's a direction. It is a behavior. It's shrinking down towards 0. That means the whole thing is going to blow up to infinity. limit does not exist. It's really, when you look at it, it's just the transformation of this 1 over x squared function, which I don't have in my library, so I don't need to worry about it. But when you look at the comparison, I'm doing this because it is a transformation of our previous example. But sadly, I don't get a number, so it doesn't exist. There is predictable behavior, but the y value isn't contained to a finite number, so we have to say doesn't exist. But I still like to describe the behavior if I can, which we then do. Okay. Yeah, no, ask as you want to ask. We have time. We have tomorrow on this as well. I'm just slowly running through all the different possibilities. So let's now start making a list here. And you can, after the fact, organize this list as you want. I'm just writing it as I think it makes sense progressively. Feel free to uh, write your own notes. That's always a good idea. And organize this in a way that you can see the big picture. Okay. The notes I write here is not maybe organized and laid out perfectly for your liking. So just be aware of that. We have touched on this simplest case in the past when my function is continuous US at the x value in question. And in the behavior limit question, that x value is where I'm headed. Then the limit as x approaches that value of my function is simply the y value when I plug in that x value. Example of that, I have an example. Very nice. Limit x goes to 1 of 5x squared minus 4. Polynomials is a very easy example because it's continuous everywhere. It's a one-piece graph. It doesn't have any strange things happening. It's just one nice and smooth line, connected line. No, it doesn't have to be super smooth. It just has to be one piece. So when I look at a behavior question first, this is the first case I'm hoping for. Is it as simple as just plugging in the x value? Because if it is, then there is no need for a behavior question to be even asked. You're trying to trick me. I can just plug it in. If I get a y value for this familiar looking function, I'm good to go. It's 1. Limit exists. They are trying to trick me. And if I were to graph it, not that I know exactly, oh, this is just transformation, right? Of an x of a parabola stretched, shift down. So over here, at 1, that's a terrible example. It's much narrower than this, isn't it? Let's say 1 is over here. There's my point. As I travel along the graph, what is the behavior suggesting happens to the y value? It's going to the y value. That exists, so there's no issue. What do you mean when you say it is continuous? You have not watched yesterday's video. We did this yesterday. It's defined everywhere. I can draw the graph with one motion without lifting my pen. It's one piece. It doesn't have like this. Now, I know I'm doing it informally for a reason, because when we define these things formally, then it distracts us from our goal here. Look at the graph. If I have to draw it left to right, I'm going to draw this, lift my pen, then draw it again. I make a jump. It's not continuous. So the basic intuitive concept of continuity is as simple as that. Yes, mathematically, things always get more technical. No, I don't need it for this course. So why scratch the surface? Do I lift my pen when I graph it? Do I make a jump? Then it's not continuous. Polynomials, it's always just one graph. It doesn't have any features like that. No jumps, nothing. Continuous. Whatever x value I'm interested in, there's a point for it. There's a y value. There's no issue at all. And I like to keep it as simple as I can to focus on the important things. But yes, if you know a little more and you sit there thinking, oh no, continuity is way more complicated. Yes, yes, it is. We don't need it. We're not going to see the complicated side of it. We're doing Math 108. Okay. So I try and keep things as simple as possible. Limits, in truth, they are horrible little things if you really look peek behind the curtain. But we don't need to. We get the job done with this approach, and it's more than sufficient. There's not going to be any question that you can't handle in this way. I will make sure of that. So we always hope for the simplest case, right? We have literally nothing to do. Asking for the behavior when the function is continuous at that x value of interest is the same as just asking for the y value. The behavior is an unnecessary layer when the function is so simple. Now, I will say while I'm here, for example, if I ask for the limit as x approaches 1 for this function, note that there is no issue there. I am containing myself around a very small window around the x value in question. I don't care what happens anywhere else. Is it continuous on that little window? Yes, it is. 1 over 1 squared. 1 exists. Move on with your life. So I'm only focusing on the window where the x value wants me to focus. Other features of the graph could be in other places. It's not relevant. And I can make my window as small as I want, just focusing right there. What is happening there? I don't care about other jumps happening way off. I'm not interested in that. So it depends on the question. It depends on the x value that I am going to. I only worry about that one. Okay, simplest case. Great, if I get it. But chances are I'm not going to. Though it could happen, I do want to start by checking that first. Now the question is, what else can happen? Okay, so here is, I don't know if I can really order these. Let's just look at an example of something else that could happen. And here, definitely ask if you are not sure, because I might not say things at the time you want. I might not say things in the way you want. I can't see your expression if it's confusion or you're good. So you have to let me know. Let's look at this function. Sure, rational function. Great. X goes to 2. I try the form. Absolutely, I would. Though, look at other textbooks. That's not what they tell you to do. I will always do it because it is always informative. However, when I look at this, I get the numerator goes to 0. The denominator on its own goes to 0. Well, that is not necessarily very informative. 0 over 0 is not 1. If you do that, or if you want to do that, then there is a severe lack of understanding about how numbers and fractions work. It indicates behavior, and that's the question. So now, just like the infinity over infinity case, it's a matter of how fast these two are shrinking relative to each other. Do they balance each other out? Does one shrink faster than the other and dominate the fraction? I don't know. So the exact same situation is happening here, but now for shrinking down to 0 instead of blowing up. So I can't say anything from 0 over 0. But it does tell me. So this, we'll see more examples of this, but this is my other indeterminate form. That's an I. Oh, wow, my writing is horrible. Indeterminate form. In that it's not clear what the behavior, what the limit answer is. And we'll see soon enough, it can actually be literally anything can happen with 0 over 0. It doesn't exactly determine the answer. But all that means is I have to be a little bit more careful. Look at, just like for infinity over infinity, look at the function I have to work with here. Oh, it's a rational function. But it's not an infinite limit, so how I handle it is different. In this case, I'm going to try and factor this guy. See if that clarifies things, because I see the top is a difference of two squares. So I can factor that as x plus 2, x minus 2. I understand as I go, yesterday as well, perhaps you find that I'm speaking very quickly. And it's because there are a lot of little variations I need to get through. You have the video, watch it again. Actually, you can probably adjust the speed in YouTube as well. Slow it down, do whatever you need to do. Okay, you don't have to get everything in real time all the time. Okay, there's just, if I don't cover all the little variations, then you're missing out. I'd rather have this be complete, since there will be a record afterwards. You can repeatedly watch. Okay, but still feel free to interrupt during the session as well. Okay, so now what is this telling me here? This function, I can see a little bit more clearly that the x minus 2 piece, I call it a piece, it's a factor, I know. The x minus 2 factor appears at the top as well. Now I cannot say, let's say here, note, x squared, the function x in its original form, is not equal to x plus 2 when I cancel these two, right? Which I want to do. That is not true. They're not the same, because the left one is not defined at x equal to 0. The right one is. They're not the same function. However, that's not my question. My question is on behavior. So my question is, how do these behave when I'm not at x equal to 2? Well, they're going to behave exactly the same. And the only difference between these two, if I were to graph them, let's do this one over here. And let's do this one over here. There is a very subtle technical difference only between these two. This one, of course, is a straight line, x plus 2, like that. This one actually is almost identical, except it has a little hole that it jumps over when x is 2. It's not defined at 2, but it's not defined in a very different way compared to this 1 over x squared. Very different. And that comes out whenever, oh, I can't see everything. Whoopsie. Whenever whenever I have this cancellation effect, what is really happening is I have this little hole that it jumps over. Little hole. It is a discontinuity. It is a jump in the graph. There's bad things happening there. But when you look at it overall, it's very localized. It's not as big a deal as this guy was, where the y values blew up. When I ask for the limit, I'm asking for the behavior only, which means I'm asking for, forget what happens at 2. You have blinders on. You can't see it. It's dark there. You can't see it. As I travel, I've lost my writing ability. Nothing is happening. Why can't I write anything? Oh, I was white, that's why. As I'm traveling along the graph by getting closer and closer in the x value, what is the y value? What is the graph suggesting happens? Am I going to a specific y value? Am I stabilizing? Yes, I'm going to this y value right there. That's what the graph is suggesting. The closer I get to 2, the closer I get to that little hole. I'm never going to be there. I'm looking at the behavior. It's a completely different question, right? Oh, well, okay, not completely different, very similar, but not the same. So by having limit in front, I'm asking the behavior of this function, well, it's the same function, I can now say is the same as the behavior of the function I get when I cancel the two pieces, because I'm not at x equal to 2. I'm not actually going to plug in a 0. They behave the same everywhere else. And all I really need is a window around 2. Do they behave the same around but not at 2? Yes, they do. The only reason these two functions aren't equal is because of what happens at x equal to 2. And when I look at behavior, I'm not at x equal to 2. Therefore, their behavior is the same. But now I've reduced this and made it much simpler, where I can look at a function that has the same behavior, but is much easier. Polynomial. Super easy. Plug in a 2, I get a 4. That means this y value that it wants to head towards is a 4. It'll never get there. The behavior question never puts me at the x value. It's just getting closer and closer to the x value and then asking, what is the y value? What is the graph suggesting is going to happen? I can't see what happens there. It's suggesting I'm going to 4. I'm happy. Everything's good. So in these cases where there's sort of a technical problem at the x value, the behavior question becomes more relevant, showing that there's no major issue. I just can't be at 2. Everything else, stable behavior. It was more of a technicality because I couldn't divide by 2, right? All right. We're making progress. There's more to do tomorrow. Just see all the variations, especially with the indeterminate form. But we'll have to pause here for now. Are there any questions so far about the, how should I say it? Slowly the limit concept is expanding by seeing more examples. Whoopsie, sorry. By seeing more examples. Just try and keep track, rewatch things, listen to things again. You're not expected, like I said, you're not expected to get everything first time. That's unreasonable. These things take time. And by tomorrow, we should have a big picture. Look at the problem book here. Okay, so everything in 2.1 for sure we could do. 2.2, I'm hesitant. I'd rather get tomorrow under my belt first to have all the examples that we need to have, get a good big picture. If you need to catch up, just focus on 2.1 first, I would say. Let's not get ahead of ourselves when we haven't done all the examples. Especially with the 0 over 0 form, there's like 5 different possibilities. See them all first so that we're not surprised by anything. We have a reference. We can go check, okay, this example, okay, I can match it with something that I've seen before and can listen to in a video. So I'd say everything up to 2.1 and patient. It'll pick up speed eventually. Righty, another session down, inching our way towards calculus, slow and steady, but we'll get there again. Rewatch things over and over and over until they start to sound better, until they feel better. Until tomorrow then.